everyone, welcome to number 45 Q-Chem webinar. My name is Kuan-Yu Liu. I'm a staff scientist here at Q-Chem Pleasanton. It's my pleasure today to introduce our speakers. For our first speaker, if you watch our previous webinar, you may be familiar with Dr. Menger. Max got his PhD in theoretical chemistry in 2019 under supervision of Professor Benedetta Minucci and Professor Leticia Gonzalez on multi-scale approaches for the live harvesting systems. His work led to several high-quality papers as well as the honor added to his PhD degree. Since graduation, he has been working with Professor Shirin Faraji at University of Groningen. Dr. Menger, as a main developer of PyServe, has contributed to various computational chemistry softwares, including Q-Chem, Shark, Theodore. Our second speaker is Dr. Vale Cofer-Shabica. Dr. Cofer-Shabica completed his PhD in physical chemistry with Richard Stratt at Brown University in 2018. His work that connects reaction dynamics to potential energy landscape geometry was awarded the Potter Prize for dissertation of outstanding merits. Then he served as director of education for the Banneker Institute of the Harvard-Smithsonian Center for Astrophysics. In 2019, he joined Joseph Subotnick Group at University of Pennsylvania, where he works on bridging quantum and classical descriptions of energy transfer in condensed phase. Current projects include energy transfer at metal surface and its excitation transfer in photoactive systems. They will be speaking to us today for chemistry does not happen in vacuum, bringing advanced solvent environment to Q-Chem for dynamics and more. And without further ado, Vale, it's yours.
All right, thank you, Kuan-Yu, for that very kind introduction. So the focus of our talk today is really just what we say, thinking about how chemical reactivity is influenced by its environment, and we're going to be talking specifically about a tool that Max and I have been developing to enable including a solvent description in systems inside of Q-Chem. And we expect to be able to do dynamics as well as sampling and other explorations in this fashion. So the sort of outline for today's talk. First, we're going to try and convince you that you should care about a solvent or about an environment. I imagine that a lot of the folks on this call are gas phase people, or people who at least we don't necessarily think that we deal with the solvent all that much. And then once we convince you that the solvent is important, we'll say, well, you have all these atoms now. How are we ever going to compute anything in such a large system? We'll introduce quantum mechanics, molecular mechanics, a hybrid system for treating such systems. And then we'll talk about this idea in the specific context of our poorly named software package. I say poorly named because it does a lot more than it says it does, GIFS. And then at the end, we'll show you a very brief application demo that we hope gets people excited about some of the things that you can do with this software. All right, so first, why care about the solvent or the environment? So again, I imagine that a lot of folks here have done gas phase electronic structure before, and small systems are pretty tractable with quantum computing codes, especially things like Q-Chem, and we can compute single point energies and gradients and couplings and for ground state and solid state surfaces, and all this is very good. Unfortunately, in most cases when we're doing that, we're not paying any attention to what could be around our molecules. They're sort of trapped they're trapped in the absence of anything else around them. And there are a lot of important phenomena that show up as a function of whether or not something is in an environment. Thinking about something as basic as a spectrum, the quality or the character of a solvent can really drastically change a spectrum. So the solvatochromatic shift is the effect where, based on different solvent, what solvent you immerse a chromophore in, you can have changes on the order of 1/10 and up to 1/3 of an electron volt in the position of your spectrum, and that's something that you wouldn't be able to predict at all in a gas phase environment. Speaking a little more generally, the sort of the prototypical example of why we worry about, or one of the reasons that we might want to worry about solvent, is in thinking about electron transfer in a solvated system. So Marcus theory. And just to remind everybody, sort of why we're thinking about this. Suppose you had a system where you had a charge localized on some donor species, and there was a nearby acceptor species that was neutral. You could imagine constructing you can imagine thinking about the energy surfaces in terms of the orientation of solvent, and those energy surfaces will be different for the system when charge is localized on the donor and when the system or the charge is localized on the acceptor. So the solvent coordinate down here corresponds to different orientations of the solvent. You might think about how strongly ordered the solvent is with respect to the acceptor and the donor molecule. And on the left-hand side of the screen, where we are looking at a place where the solvent is highly ordered with respect to the donor, and on the left-hand side of the screen, highly ordered with respect to the acceptor. That happens because we have charge, or in one case the donor is charged, in the other case the acceptor is charged. Now we can't just hop between these two, as if we look at the energy when if we construct a diabat for when the charge is localized on the donor, when the solvent is ordered with respect to the donor, that's right here, and the donor is that's a stable configuration. If we still have the charge located on the donor, but we are ordered with respect to the acceptor, then the energy is way up here. The reverse is true if we are on the acceptor. Now, energy conservation means that we can't just jump from this configuration to where energy or the charge is localized on the donor to the acceptor. That would mean injecting energy to move from this point all the way up to this other diabat here. And so instead, what has to happen is that the solvent has to reorganize itself and find some configuration where the energies of both electronic characters are the same, and that's this crossing point right here in the middle. And so Marcus theory is really, it's a reminder, or should be a reminder to all of us about the ways in which solvent can gate electronic motion. It's sort of the opposite of what we usually think about in the Born-Oppenheimer approximation. But when we're dealing with highly non-adiabatic problems, and that's the kind of thing that we want to be able to think about, particularly in the presence of a solvent, then the motion of the solvent is almost everything. Last example I'll give is, or just to talk about why environment matters. I'm gonna make the claim that this is really where the action is for a wide range of systems, from photosynthesis to proton-coupled electron transfer near an electrode to other more general catalytic processes. All this stuff has to happen in the presence of a solvent. And to give a little bit more in terms of thinking about some intuition for this, something like if you think about the green fluorescent protein, which is what gives these jellyfish their very interesting color. If we try and study this protein in this chromophore in isolation, this protein is very floppy, and it can rapidly explore a large area of phase space upon excitation. and we'll immediately find a conical intersection and relax, no fluorescence. If instead you embed this chromophore in this protein superstructure, then the system will be frustrated. It'll be much more rigid, and it'll be frustrated in its attempts to find a conical intersection, and then we'll have to follow some other kind of relaxation pathway. In this case, an emittive one, and it will fluoresce to relax, or for the energy to relax. So being able to think about the environment, whether it's a solvent in terms of liquid or just a protein superstructure, is really important in understanding the dynamics that happen in our systems, particularly when they can be when the character of our systems can be so strongly modified by the environment. This is a case that right here where the energy landscape is modified by the environment. In the Marcus theory picture we talked about before, the energy, the charge. You think about the stability of different charge states or electronic states being modified by the environment. All right. I think Max is going to talk a little bit about the way that we about the ways that people in general in the past have brought solvent environments.
Yeah, so basically the next part is, if we have a system like this green fluorescence protein, right, where we have 100,000 or millions of atoms that we want to consider, of course we cannot treat them these days quantum mechanically, right? So instead, what people use in the past or use nowadays is molecular mechanics, where basically you solve Newton's equation of motion, and you also describe your system classically in terms of a parameterized force field, and therefore you can really compute very large systems and do simulations of longer time scales in a few minutes, even on a normal PC that we have, this and this basically leads to the next. So how the whole environment, or if you want to treat a large system, then you basically have to rely on such approximate methods, because everything else is simply not possible these days. And just a reminder what we typically deal with. So you describe your system in terms of these parameterized force fields that that can be where you basically have some functions and some parameters that you derived somewhere, or you took your favorite force field from a force field database, and you describe your interaction energy of your system in terms of these penalty functions. So you'll say you have some interaction with some favorite position for your bond term or for your angular term and so on in the system, and every time the system's basically out of that equilibrium position, you pay some kind of penalty function, which is this potential that you see here. And and you can basically distinguish that into bonded and non-bonded terms. And the most difficult part here is basically how do we derive those force fields, and the easiest way, of course, is we let somebody else do that work for us, and we simply take an existing force field. And actually, to hereby in some of the one of the following Q-Chem webinars, one of our co-workers here in Groningen will present a way how you can derive a force field automatically from a QM calculation using Gromacs, Q-Chem. Sorry. Okay, right. So now we know how we can describe large systems, but of course this description is very limited. So we cannot simulate unless we have something like a reactive force field, something like that. Really chemical interesting processes like bond breaking and so on, because, well, all the potentials for the bonded terms that we have in the system are usually just harmonic parabolas. So, bond breaking is not within the capabilities of the force field, but that is where the real chemistry happen, right? And what this leads to is it's basically that one still has to fall back to quantum mechanical description of those properties. But again, you don't want to treat the whole system at the QM level because that's simply infeasible. And therefore, you do a partitioning, right? Because in most cases, luckily for us, the process that we want to study is quite localized. So you can distinguish the system into an active site where the process that you want to simulate happens, and the environment that has an influence on the active site but doesn't participate directly in the underlying process, right? So like in the example that Vale gave before of the green fluorescence protein, the environment forces the structure of that protein to be in a certain position, and it tunes its excitation, excites but due to the background charge, basically, that the environment represents. But in the process of the fluorescence and so on, it doesn't take actively part, right? And and there are different ways of, so if you if you have the partition into QM and MM region, basically, the interesting question is, how do you treat the interaction energy between those, right? That's kind of now the most prone question that remains. And here there are several ways of doing that. The simplest is mechanical embedding, but the state of the art is what we talk about now. It's electrostatic embedding, basically, and there you simply say we have our Hamiltonian that describes our QM region. That can be anything, and we just add the MM in terms of point charges. So therefore we get 1 electron terms additionally to our Hamiltonian, and then we solve our normal time-independent Schrödinger equation.
And just to interject, these charges aren't things that we have to make up. You know, whenever someone made up those force fields before, then they made up those charges at the same time and fit them all to represent whatever solvent it was they wanted them to, or whatever environment it was they wanted them to.
Yeah, so the charges are simply they are to include this interaction between the environment and the system. And basically in all of those simulations, you care about 2 things, and one is the interaction energy, and one is basically the force on the interaction energy, right? And in the case, if you have if you included this electrostatic embedding, you can do a very simple trick. So you can say the force of the interaction energy as on the M side is basically the charge multiplied by the electric field due to the QM region on that side. And luckily, most electronic structure codes, for example, Q-Chem, have already via their input an option to compute all of that properties. So you can say, I have external charges to my system that's surrounded, and additionally you can say, please compute at certain positions the electric field, and therefore you can very easily include a basic QMM scheme into your system or for yourself, basically.
Great. So now we're going to start talking a little bit about the program that Max and I have implemented, and we want to point out that, and we know there are that we are only enabled to do this in Q-Chem because of the heroic efforts of people like John Herbert and Yihan Xiao, on all the work to make things like external charges, like Max was just talking about, for an electrostatic embedding part of Q-Chem, and the work that Yihan has done for the charm interface inside of Q-Chem, and so first, I just want to say our great thanks to those folks and others, and I apologize if I miss anyone, or not if, surely I miss people, but so we're very excited to be able to use those efforts and try and maximize the potential of their work. I mentioned at the beginning that our program kind of has an unfortunate name. GIFS. GIFS is Generalized Interface for Surface Hopping, and this should be a reminder to everyone, not to limit yourselves when you're choosing names for things, because while it was surface hopping that we first started thinking about, this is really a tool for studying non-adiabatic processes in the condensed environment in all kinds of ways, and so that may involve doing dynamics on diabatic seams. That may involve doing umbrella sampling to compute potentials of mean force. There's a whole lot that is possible with this tool that we limit in some ways by calling it GIFS. We're going to try and show some of those things today. But since the title or the name of the program includes surface hopping, we want to talk a little bit about surface hopping and describe the way the program works in this mode. And again, surface hopping is a solution to the problem where you say, okay, I have, in general, we talked about doing dynamics, doing F equals ma over and over and over again. And this is that's a thing that we can do when we have a single electronic surface that we're on. Suppose that we were just on a ground state surface, we were just on an excited state surface, and maybe those surfaces were so well separated from each other, as they are not in this case, but so well separated from each other that they wouldn't talk with each other at all, and there would be no coupling between them. That's the Born-Oppenheimer approximation, that the electronic surfaces are, or that's it's the essence of the Born-Oppenheimer approximation, that the surfaces are not going to talk to each other. The electronic surfaces are not going to talk to each other. But when we find ourselves in a situation where the electronic motion can be where there's a region where nuclear motion and electronic state are tightly coupled to each other, it's possible after some kind of excitation to an excited surface to end up not on that surface anymore, to end up back in the ground state in some configuration or another. And being able to track these nuclear relaxation processes is something that, or these electronic and nuclear relaxation properties is something that we'd like to do without doing full wave function dynamics. I mean, notionally we could, but Max and I have been trying to convince you that we need to worry about bigger and bigger systems, and coming in and saying, well, all right, now we have to do wave function dynamics is not the way for us to do that. And so surface hopping is sort of a trick where we solve Newton's equations, F equals ma again, but instead of doing it on a single surface, we allow our surface to change. And so at the beginning, we might come up for our excitation and then roll back down, and then as we come to regions of configuration space where the electronic surfaces are strongly coupled to each other, we have to figure out whether or not we stay on that surface or we switch to another one. And the way that we do that is by propagating the electronic wave function in an adiabatic basis that is parameterized in terms of the nuclear coordinates. So here, this is an adiabatic basis for our system where that is actually coordinate dependent. And so everywhere in configuration space, this adiabatic basis will be different. If we plug this expansion in the time-dependent Schrodinger equation, we come up with evolution scheme like this, or a differential equation for evolution of the electronic wave function. And we have some tricky terms in here. One of those tricky terms is the derivative coupling. And now I will say that there are a number of different schemes for choosing when to hop between surfaces. In the particular version that we implement, we use Tully's fewest switches criterion, which computes probabilities for hopping in terms of the electronic density matrix. I say that there is a tricky term here, is this derivative coupling term that's right here. And one of the things that makes doing surface hopping calculations in large systems really problematic is that this derivative coupling term is very expensive to calculate. And the number of derivative coupling terms that you have to calculate goes up with the square of the number of states that one wants to study. And so a couple of years ago, and we're really borrowing from a technique developed by Meek and Levine, where the Subotnick group put out a paper describing what we call an efficient algorithm for computing surface hopping in situations where you have many states, or even states where even times where you just don't want to recompute the derivative coupling over and over again. And this uses a wave function overlap scheme. The wave function overlap scheme, again, this idea inspired by Meek and Levine, is really wonderful because it is faster, because we don't have to compute the derivative coupling except when we are actually transiting surfaces. We have to do that to be able to figure out where to deposit, or where to inject, or where to extract energy from as we are hopping between surfaces. So it's faster because we're not calculating a derivative coupling at every time step, but it's also better. And it's better because we don't have to worry about the trivial crossing problem in the same kind of way, where you have two states that cross each other, but in a very small coupling region. The coupling region might almost be infinitesimal. And if you're using a derivative coupling approach, you will miss that as soon as you hop from one side of the interaction region to the other. You'll be in there won't be anything driving a hop, and you'll miss it. And this is would be this is unfortunate. And so this wave function overlap scheme captures those effects by computing this t on average over the course of a nuclear time step. Okay. There are a number of subtleties for dealing with surface hopping that I kind of alluded to already, and so I just want to point out a couple of papers that folks might be interested in looking at for understanding the way that we have implemented things in this program. The first, again, has to do with avoiding the derivative coupling. This is inspired by Meek and Levine, but this paper that Umber, who is a postdoc, used to be in the Subotnick group, worked on, is now a professor in India. This paper right here talks about that. A very talented graduate student in our group, Zayu, figured out a scheme for dealing with the phase matching problem when it's not entirely clear. If you do an electronic structure calculation, you are free. You have free in terms of your choice of sign of your wave function. But once you are looking at wave functions at different time periods, the sign is no longer determined. But you can uniquely determine this u in terms of minimization criteria. That fixes the signs of each of the wave functions. You can see that in Zayu's paper that came out earlier this year, and we implement that in our program as well. And then the last thing that is very exciting is that Hongshe Tai, who is also a graduate student in the Subotnick group, has a scheme for a CIS scheme that adds one double that enables us to get around Berlin's theorem, or Berlin's interdiction rather, on S0 S1 coupling. And so this isn't, I'm sorry, this isn't, this is a little bit of a tease. The paper's out, but this isn't into the Q-Chem release version yet. But hopefully sometime in the next 6 or 8 months, we'll have code that allows us to calculate CIS +1 double derivative couplings between the ground state and excited state surfaces, and also this will also of course work with TE-DFT. All right.
Okay. So after this nice introduction from Vale to surface hopping, the title of that talk was basically how we include also the environment, right? So how do we do that in surface hopping? And let's say the most basic way on that is simply, well, instead of computing energies gradients and non-adv'd couplings and all these properties, using just an electronic structure code, we now use a QMMM scheme to compute all of those things. And in fact, a lot of the existing surface hopping codes like Shark or Newton X have a QMMM scheme in exactly that fashion. So what are we trying to do differently than these people? And our idea is basically the following: there are already a lot of existing high quality molecular dynamics code that do simply by solving Newton's equation of motion and computing energies and gradients using some molecular mechanics force field, right? And some of those codes also provide already a QMMM type interface where you can do ab initio Born-Oppenheimer type dynamics on a single surface using QMMM. So our idea was basically, can we modify such a code, or can we extend such a code using our own basic software, so that it actually can do not only Born-Oppenheimer QMMD, but also other non-adiabatic dynamic schemes. And like Vale said, we picked that a bit unlimited name because, well, our basic idea at the beginning was we want to do surface hopping, but as we'll also point out later, it's not limited to that at all. And yeah, so the idea is we provide a very easy interface between, in our case, Gromacs as our MD software and Q-Chem as our electronic structure code. And just for those that don't know, a brief introduction in both. So Gromacs is a classical MD code that can do force field type calculations, and it's around. It's an open source code that is around for several years now, and therefore it supports a wide variety of different force fields. It has multiple propagation algorithms implemented, including thermostats and barostats that you can include into your simulations. And as it has also a large user base, it also provides an extensive suite of trajectory analysis tools for you. And additionally, it has all these ground state free energy calculation tools implemented. And well, also it currently it had basic support for QMMM, but with their newest update they broke that, which is but they want to have it back.
So they are going to fix it.
They got in the new release. They want to have a new, much better version of what they of the version that they had before. Okay, and yeah, and then Q-Chem, as I probably don't need to point out to many of you folks, is a general purpose quantum chemistry code. And the very nice thing for us of Q-Chem is that for non-abiotic dynamic simulation, you basically need analytic gradients and non-abiotic coupling vectors, and Q-Chem provides that on a huge variety of different methods, ranging from configuration interaction to linear response, time-dependent DST, to couple cluster and more on that. And as Vale also pointed out already, Q-Chem also provides with several implicit and explicit solvation schemes, which basically means that they have the thanks to all this work of Yehan and John Herbert and others, they already have all of the utilities that you need, that we needed for our code. So we could simply, we could very nicely build on top of theirs without doing too much work on that side, and we could simply take advantage. So yeah, so our code basically takes the parts of Gromacs for treating the environment at an ML level and using its advanced nuclear propagation schemes and combining that with Q-Chem's huge capacities of doing electronic structure calculations. Yeah, to really include the environment, right? And yeah, so now comes the why is our system not limited to surface hopping, basically, and just what the basic software package is about to do. I hope to explain in the next, right? And therefore we have like three components, right? We have an MD code, which is in our case Gromacs. Then we have our interface in the middle, our code in the middle, and then we have an electronic structure code, which is here, Q-Chem. And molecular dynamics, in fact, I basically broke down to three steps. So typically it's implemented either using a velocity Rayleigh or leapfrog scheme, but we, for reasons, we restrict ourselves to the velocity Rayleigh. And if you break that down, you have three steps, which are we change and update the coordinates, then we compute the forces at that point, and then we update the velocities of the system. And this is in a loop, right? So what did we have to do to basically do normal Born-Oppenheimer MD? That is simply we have to compute the forces at a QMMM level on some part of the system. So therefore we have to tell basically Q-Chem to compute energies and gradients of a given system in an environment, and we take Gromacs QM scheme. And with that we can do we can solve Newton's equation of motion on a single surface, right? But we are not limited to that, in fact, right? So as Vale described it before, surface hopping is basically solving Newton's equation of motion for a given potential energy surface, but that surface can change over the time, right? And or depending on the propagation, so your system can jump from one surface to the other. And for the basic algorithm of the MD software, the only thing that changes at those jumps is that you have to rescale the velocities to have energy conservation, right? Because else you change your potential energy by changing your active surface, but you're not updating the velocities accordingly. Okay, well, so yeah, so therefore we came up with that framework that basically has two different hooks into the MD software, which is one to update the gradient, so compute the gradient using something, and here we do in case of surface hopping, or in case of surface hopping, or even if you want, which is not yet there but could be we are working on implementing. In case of air and phase dynamics, you would do an electronic propagation of your electronic wave packet and decide, so compute the gradient depending on the solution of your electronic problem, right? And then in case of surface hopping, basically you also call the rescale velocity function, which might need you to that you need to compute a different the gradient of a different potential energy surface, and therefore you have to call again Q-Chem in this case, right? And if we so we can basically switch between very simple ab initio molecular dynamics, where we just compute the gradient on a given within a given framework, to up to over and phase dynamics up to surface hopping in a single framework that can basically switch out on using your input. So you just update your input file and you can choose all of these systems. And and this is basically the structure of the code. So we have this GIFS interface layer with two different function hooks that were up compute gradient and rescale velocities. And then you have basically you select basically your nuclear propagation scheme. So if you do Born-Oppenheimer MD, then you just compute the forces, and the rescale velocity does nothing. In the case of surface hopping, you also do the electronic propagation on top, and you then decide if you need to rescale the velocities or not, right? And therefore, therefore you can basically implement also every other scheme that propagates the nuclei classically according to Newton's equation, and then computes a gradient or something, the gradient based on some scheme, right? Like in air and phase, where you have a linear combination of different forces that you use. And everything can be, every algorithm that works in that way can be implemented using that. That's why the calling it a generalized interface for surface hopping is a bit limited, right? So so currently what we have is you can do Born-Oppenheimer MD. You can also do few switches surface hopping, and we're currently working to have the augmented fuse switches and the air and phase also working, which is with the function that we have, shouldn't take too long to do that. Of course, you can also use it to do just gas phase molecular dynamics, but the main benefit that you will get is if you take advantage of the capabilities that Gromacs has and you do QMMM, of course. And for developers, maybe the nice thing is that we provide a very generalized interface to Q-Chem to do single point energies, gradients, and non-embedded coupling computations, and you can extend it to your own scheme that you want. And currently we also have basically a Python and a C and a Fortran interface. So if you don't like Gromacs for some reasons, or the capabilities of Gromacs are limited for your special reason, in principle, you can use that to extend your own or your favorite molecular dynamics simulation software to do the same calculation in a very straightforward manner. Okay, and yeah, with that, well, we come to real chemistry application at the end after a very after a long talk about basic schemes.
Yeah. So I'm sure people are interested in what we can actually do with it. So I want to point out first, we're going to talk a little about DMABN, dimethylamino-benzonitrile, and say that this is a system that has been beaten to death for a long time, and there are still open questions about it. And today we are not going to resolve any of those open questions. We're simply looking for an interesting system where we could test out some of our ideas. But in any case, so this is a dual fluorescence molecule, which means that there are two different relaxation pathways that occur on different time scales, and those come from either from a uniform excitation that is over the aromatic ring and then extends off of it in both directions, or a charge transfer state that transfers that has charge transfer from this nitrogen to the aromatic ring. And both of these different states have very fast lifetimes. We know that there's the S2 to S1 transition through a conical intersection less than 50 femtoseconds. However, in the presence of a polar solvent, the dipolar charge transfer state is stabilized. And some work that was done in our group a number of years ago showed that with one quantum mechanical acetonitrile, you could already start to see some of these effects. And yeah, so we know that there are these two states. We know that they are somehow entangled with each other, and we'd like to be able to study them in the presence of a solvent. And we know that one solvent, or one molecule, a solvent does not make. And so if we want to look and sort of see what's going on, I'm going to switch screens now. So I'm going to start playing a movie in just a moment, but to orient you, this is DMABN surrounded by a whole bunch of acetonitrile solvent. The DMABN is described in Q-Chem using a relatively straightforward Hartree-Fock scheme, and CIS for the excited states. And around here, we have transition densities that are plotted in terms of whether or not we are looking at the first state or the second state. So the red is the second state, and the yellow is the first state. And so there's an immediate rapid transition. And I understand that on your screens that this is not nearly as smooth and as cool looking as it is when everything is when everything is going like it is over on my side. So I'm sorry for that. If anybody wants to see the video or talk about it, happy to pass it on or answer questions. But there are a couple of things that are really interesting here. So we can see, or we're actually watching a surface hopping calculation taking place inside of a solvent environment. We can see the electronic, the transition densities shifting as a function of time. And this is a really powerful tool. So this, I think we probably have about 500 solvent molecules in this box, and we computed, and again, I think 19 or 20 quantum mechanical atoms, and we computed this whole thing in just 18 hours on a single node, on a single node from 2012. Our new system calculates things at least twice this fast, and this was really only possible because of the parallelization efforts that John Herbert and others at Q-Chem have, and other developers at Q-Chem have done. And so it's really a testament to the to why we would want to use Q-Chem and work with Q-Chem in the first place, just because of how fast and how fast the codes are, and how diligent people have been in bringing new and interesting electronic structure methods to the system. And I kind of, one of the ways I kind of think about what we're doing, again, we're not, we know there's a lot of dynamics functionality already in Q-Chem, And we're not trying to replace that or step on any folks' toes there. We also recognize that there's a whole StatNet world out there, a whole StatNet community that we don't want to try and duplicate in terms of thinking about sampling schemes and algorithms for propagating systems in different ensembles. And being able to marry like the really excellent electronic structure features of Q-Chem to those algorithms is what makes this so exciting. Also, you know, people at Gromacs were super accommodating of us in our time. Max and I were welcomed in the middle of the Finnish winter by Gerrit Konov and Dmitry Morozov at the University of Jyväskylä, and they spent lots of time with us to talk about what we were doing. And one of my hopes is that this program can be a platform for introducing more people to Q-Chem who wouldn't have run into it otherwise, and this could be a way of you know, reaching out across communities and saying, oh, here's this software that you might not know about that would be interesting to work with. For the rest of our acknowledgments, I really have to thank enormously Joe, who is my supervisor, Joe Subotnik at UPenn, and Shirin Faraji, who is at University of Groningen with Max. They've been super supportive throughout this process, and it wouldn't happen without them. Also, I have to really thank Yihan Xiao, who has been incredibly generous with his time at all possible junctures, and has taught me an enormous amount about the internals of Q-Chem and getting our code up and running and talking to it. This is the rest of the Subotnik group right here. Didn't have time to get a picture of the Faraji group in, but these are the people that you know, that in the middle of this, you know, this strange world, you know, they're faces that we get to see from time to time, and it's important to be able to see people's faces so you don't go too crazy. And with that, we'd like to open it up for any questions and say thank you so much for your time and attention. And yeah, we hope that this was interesting.
Thank you, Vale and Max. It's a really interesting talk. Got our first questions. Just want to remind you, feel free to submit questions if you have more. So what versions does GIFS support for Gromacs and Q-Chem?
So Gromacs, so support in Q-Chem landed in the trunk a couple of weeks ago, and so we will make it for the 5.3.1 release that is supposed to happen early next month. And so people who are users of Q-Chem and are able to use it as soon as that happens, and people who are Q-Chem developers, you can already use the trunk branch. And things we're very much in a beta testing phase right now, and so you know, if you're interested in using this, please contact us. I'll show our first slide, I guess, so that people can see email addresses. We would love to talk with anyone about whether or not they'd like to use the software and how they could. As far as Gromacs goes, Gromacs is in the middle of a pretty big rewrite right now, upgrading to new infrastructure, and the suggestion that we received from Dmitry, who's worked on Gromacs for many years, was that we use the 4.6 branch of Gromacs, and so to make our hooks into Gromacs, and so the 4.6 and that whole lineage is where we are. And so I think, you know, Gromacs has shifted over to an annual or a release cycle that uses the year to encode the version, and this will be a couple of years back, but we have patches available. The Gromacs team has also been super receptive, since our code makes such a you know, a small incision, as it were, into Gromacs. It's only a couple of lines they need to add to support our interface, and we hope that, you know, in Gromacs 2021 or thereabouts, we will have mainline support, but that all depends on how rapidly their transition takes, and they are a research community that's been working together for 30 years at this point, and so they move it at a pace that is their own.
Yeah, thank you. So next question, what is the boundary condition used for the DMABN solvent simulation?
Great. So the boundary, so this is a droplet model, basically. This movie took a long time to render because of bringing in all these surfaces. So I can't zoom out and show you right now, but we're in a droplet. And so we're not using periodic boundary conditions or anything like that. This is 1 picosecond, and so that isn't really long enough for the solvent to start evaporating on us or anything like that.
The box is large enough so that shouldn't
right.
any problem in the time scale that we want to simulate.
Thanks. So our next question, does Q-Chem only read in the point charges from the MM part?
I imagine that the question is, does Q-Chem only see is the only way, what is the mechanism by which Q-Chem sees the point charges? Is that the question, do you think, Kuan Yu, or do you have
maybe
I can tell you how it works.
Maybe they're asking what information will be passed from the MM to the Q-Chem when they do this.
Right. So each of these, I'll flip to the end here so I can point. So in the simulation here, we're using a force field for acetonitrile, and that force field includes point charges associated with each of these atomic centers, and those point charges and their locations are passed to Q-Chem, and so that is all the information that Q-Chem has, and then those point charges will again go into the 1 electron term when calculating whatever properties we ask for of DMABN.
Thanks.
And so the Gromacs takes care of all the MM part of this calculation, and Q-Chem just sees the environment as point charges. That's
as a cloud. Yeah.
Thanks. So our next questions. So in the GIFS, how does it handle the parallel scheme in Q-Chem? Like if we want to do the MPI versus OpenMP?
Currently, we only support OpenMP parallelism with Q-Chem, but we have a parameter that when we call Q-Chem, we will set the number of threads to be used across a single node. If people are looking to use an MPI version, we would welcome people contacting us about that. I guess if the reason for that is you have really enormous systems that will take too long otherwise, then that's one thing. And if people have small nodes with not enough processors, then I imagine that could be a problem too. But currently we do not support MPI, but certainly could. It would just be, we'd want some interest in that before extending a development effort that way.
And in surface hopping, we also compute an ensemble of trajectories. So typically, it's more efficient to simply run more trajectories at the same time using.
Right. However many nodes, you take however many nodes you have and stick trajectories on those, which is the embarrassingly parallel part of the problem.
Okay, thank you. If there are no more questions, I'm gonna move to close the webinar. I would like to thank Max and Vale for the informative talk. Very impressive work. If you have questions later, feel free to post your question to our forum. You can go to our website and click the Q-Chem Talk forum. I already created a topic for this webinar. Feel free to post questions here. And thank you again, Vale and Max. Thank you all the attendees for listening.
This concludes our webinar. We would like to thank Kuan Yu Lu for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.